All right, let's do this. All right, so you remember we had, I didn't give you the first law, did I? I gave you work. Anybody remember this one for work? Dio's here.
There you go.
Formula for work. Dean.
Wasn't it the integral of for thermal?
For thermal. Yeah, minus the integral of
Pressure times the change in volume.
PdV. All right. Okay. So we're going to be using that today. We also want to look at the first law of thermodynamics. Okay. Did I tell you about the laws of thermodynamics?
Let's say no.
There's 4 laws. Remember 3 laws of motion?
Yep.
Dean, first law of motion.
An object in motion stays in motion.
Excellent. Look, he's running off because I'm going to pick on him.
Go with that.
All right, see you, Dean. Second law, somebody. Of motion.
F equals ma.
F equals ma, right? Third law.
The reaction is an equal
The reaction, right? So you know those. So we're going to have 4 laws of thermodynamics. The first one is conservation of energy, which we're going to use today. It tells me that the change in the internal energy, the little change in U, internal energy, is equal to dq plus dw, a little bit of work. Now how do I do a little bit of work? Well, I just look at the differential. dw is going to be what? Minus p dv. Does that make sense? A little bit of work, it's minus p dv. Right? So this is the differential form of the first law. If you write the full out, if you integrated stuff, you would get delta U equals Q plus W. Yes, does that make sense? A little bit. Now, a little bit of notation that you'll see in some textbooks, probably not our textbook, but like when you were to take this class more advanced, when you take thermodynamics, you'll see sometimes they put lines through these dq and dw. Okay. And there's a reason for that. We have what we call state variables. And state variables describe the system, right? So some state variables would be P, pressure. So give me another one. What do you think a state variable is? It's going to describe the system as it is.
Volume.
Volume. Okay, good. Another one. I think we ought to do a gas law.
T. Temperature.
Matthew, get in on this. PV, what's another one? R is a constant. N, either little n or big N, moles or molecules, the same idea, right? U, internal energy, these are all state variables. They only depend on the state of the system, not how you got to that state. Okay? The non-state variables, these are kind of the variables that how you just interact with the environment. That's going to be the heat and the work. So heat and work depend on the path you take, or how you get from one state to another state. That's why these lines are here, because the normal derivative is state variables, and these are signifying they're not state variables, that they depend on the path. Okay? Does that make sense to everybody? Why? You're making a distinction between them?
Is Q specific heat or just heat?
Q is heat.
Q is heat.
Yeah.
What's this?
C.
Oh,
Specific heat was C. Q equals MC delta T. Right? And we're going to look at that in a little bit. Okay. So, if I have a gas and I want to change its state, right? I'm going to look at a PV diagram here. So this is my push pressure, this is volume, and I'm going to start at this location here. So I'm going to have an initial volume and an initial pressure. And now I'm going to increase the pressure on this gas. Okay? But I'm going to keep the volume fixed. This process of keeping the volume fixed but increasing the pressure and the internal energy, this is called isovolumetric. Right? So if we take that word apart, what do you think it means? Iso means
Equal.
or constant,
Same.
right?
Yeah.
Volumetric for volume. Back in my day, we called this isochoric. But I guess that got hard or something, so we don't call it isochoric anymore. That's what we call it.
And what did you say? Constant volume?
Constant volume. Yeah. So that's why I think they switched it to volumetric something.
Increasing pressure at constant volume.
Right. The pressure and the temperature are going to change, but the volume is going to be fixed. And we're doing all this under the guise of an ideal gas right now. Okay? So if I do that on this, what's going to happen? I'm going to go from here to here, right? So I'm going to go from P naught to P final, keeping the volume fixed. Right? You guys with me? Okay. In that process, what is the work? Can you figure out the work in that process? Remember, the work is the integral P dV, which means what in terms of the graph?
So it'd be 0.
Zero, because there's no area, right? It's just, there's no change in volume. dV is 0, so the work is 0. So no work is done in the process of isochoric or isovolumetric. The first law tells me that delta U is equal to what? Well, what does U equal for a gas? Anybody remember? What was the energy of a gas, internal energy of a gas equal to? 3/2. See Mary looking. Did you find it? N R T. Does this look familiar? We did this, didn't we?
The 3 has those.
3/2 NRT. When we derived the ideal gas law. We also got same equation, but instead of little n, we got 3/2 N KT. Right? That's the same. This is just molecules, moles. So that's the internal energy of a gas. We're going to use R today. So what does that mean? If I change my internal energy, that corresponds to a change in what quantity? If U is going to change, what's here is going to change?
Temperature?
Temperature, right? So delta U is going to be 3/2 NR delta T. Right? Makes sense? Jared, you with me? Sarah, you with me? Okay. What's Q equal to? If I look at my first law, what's Q equal to? What's 0 in my first law?
Delta U minus work?
What's 0 in this law? Work. So that
delta
means
U.
Q is equal to what?
Delta U.
Delta U. So Q is equal to delta U. It's also equal to 3/2 NR delta T, right? What happens when I heat this gas? What does it do? It goes into raising the temperature, increasing the pressure, but it doesn't do any work. So all the heat that I put in goes into the internal energy of the gas, right? Does that make sense? Now we can write this a little different way. If, as Matthew asked, what specific heat? Remember that before? What was the formula for specific heat, somebody?
Q equals MC delta T.
And this kind of looks like that. I have a Q and I have a delta T, right? This C, what were the units here?
1 over joules.
Oops, no, joules are in the numerator.
Sorry, joules over. It's degrees Celsius.
Degrees Celsius, and I gotta get rid of the mass, so
So grams.
grams. So we have grams per degree Celsius, right? And then down there, joules in the numerator. This we can kind of write similar. I can write this as Q equals N C sub V delta T. But this C sub V is a little different than this C. This is got kilograms, but here I don't have kilograms, but how am I measuring the amount of material? Not by mass, but by mole. So this is called molar specific heat. All right? CV is the molar specific heat. And what are the units going to be? Joules per mole degrees Celsius, right? Or Kelvin, degrees Kelvin, doesn't matter that one. Right? Does that make sense? And what is CV equal to? Looking at above, what's CV going to be equal to? Let's look here. What's left? 3/2 R. Right, so, okay, this is all the information you need for the isovolumetric process, right? We got the work at 0, We got the Q, we got the delta U, we know those. We look at the ideal gas law, what's being kept fixed. So PV equals nRT. So if V is being fixed, I can bring that over here, bring this T over here, so I get P over T equals NR over V, right? This is a constant, so P naught over T naught equals P final over T final. That's how these things are related, right? Everybody see how I did that? I just put the constant over here and brought the variable over here. So I can relate the initial pressure and temperatures to the final pressure and temperatures. Okay? So this process is important. We're gonna have 4 processes. Okay. All right, you ready for the next one?
So is it one of the thermodynamics law?
No, we're only using this law right now, the first law.
No, that's the first law.
But this is one of the 4 processes we're gonna look at how to change a gas. There's other ways you can change a gas too. I'm just looking at the basic 4. You with me, Sarah? You look confused.
Yeah.
Spelling?
No, the first law was the change in U.
Yeah, which is conservation of energy, really, right? You ever see this as conservation of energy? Changing the internal energy comes from external energy, Q and W, heat and work. So I'm just conserving energy. All right, let's try the next process. And we're gonna land a little early today because I wanna go meet our candidate
Can we
coming.
just follow you there?
Will you just go to McCarthy? I'm gonna meet him at the parking lot. That'd be a little awkward, but I'll
All in the
go.
parking lot. Bye. We need you.
That'd be a little awkward. We don't want to scare the guy. You know what I mean? I mean, you want to be enthusiastic, but you don't want to be stalkerish. You know what I'm saying?
What's his name?
Dr. Ashcraft.
What?
Dr. Ashcraft, A-S-H-C-R-A-F-T. You gonna look him up?
Yeah, ASH what?
A-S-H-C-R-A-F-T, Ashcraft. That's awkward.
Stalkerish
Wait,
and
you looked him up before
enthusiastic.
you brought him here, right?
Yeah.
Yeah, okay.
Okay. PV, right? So here's V naught, here's P naught. Okay, now we're gonna change. We did what? Last one was constant volume. Now we're gonna do constant pressure. So that process is called isobaric. I can't spell. Like barometric pressure. Isobaric. Right? You heard of barometric pressure, right?
Barometric.
Yeah, that's the barometric, measuring the pressure of the atmosphere. So isobaric. So constant pressure.
Constant pressure.
What's that gonna look like on this diagram? What am I gonna do? Constant pressure. Sarah, what do you think?
Just the horizontal line.
Horizontal line. Exactly. I'm gonna go to V final. P doesn't change, right? Isobaric. So in this process, delta P is here. You with me? Okay, what's the work in this process?
Yeah.
Nope. How do I calculate work?
So negative V initial,
Yeah.
V final minus V initial.
Yeah. If you think in terms of calculus, it's just what?
There.
That area. That's a rectangle. So the work is minus P delta V. Right? That makes sense? You with me, Matthew? Yeah. P is the height. Delta V final minus V. This is delta V. That's the width. That's the work. Okay. What's delta U? You shouldn't be able to tell me that.
Q plus work.
Okay, but in terms of the state variable, T, because you're telling me in terms of non-state variable, tell me in terms of state variable,
3 halves of nRT.
we have then our delta T. But
That's it.
still, the internal energy only depends on temperature. So, the internal energy, the change in energy has to be equal to the 3 halves NR, the change in temperature. Or I can write this as N CV delta T. Right, you with me? Temperature determines the internal energy. It's the only thing in an ideal gas. That's what we're dealing with. Right? Okay. Can we find the heat? Is the heat the same or is it different? It's going to be different. Look at the first law. What is the heat according to the first law? Let me put a line here because we're going to do some derivations.
The internal energy minus work.
Excellent. So Q equals delta U minus the work, right? Well, delta U I know. And CV delta T, right? And I know minus the work. What's minus the work? Minus a minus P delta V or plus the P delta V.
Is that an integral still?
Well, if I integrate this, P is a constant. So I have the integral, pull the P out, minus P delta V. The integral of delta V is just V final minus V initial.
I know, but like in the, under the green line in that equation, they were all changed in initially. Do you remember that?
All right, so when I integrate dq, I just get q, the total heat.
Okay, so we
And then d, because these aren't state variables, so they don't change, really, it's just a little bit. Do you see what I'm saying?
yeah.
This is a change because it's a state variable, it's changing. So that's why the lines over there signify it's different. Good question. All right, so we have this. Okay, let me erase that. So we need to express this in terms of temperature only, not volume, so I want to get rid of volume. So how am I going to do that? I'm going to use the first law. First law. Or not first law, sorry. I do a gas law.
Oh, PV equals nRT.
PV equals nRT. So I'm going to rearrange this and get V.
V equals nRT divided by P.
Okay. That's a sloppy P. So I can calculate delta V. Delta V would be what? V final minus V initial, right?
Sure.
Thank you. nRT final over P minus nRT initial over P. What can I factor out?
NR.
nR over P.
P.
nR over P delta T. So I can replace delta V with nR over P delta T. So this becomes NCV delta T plus P times nR over P delta T. That's my delta V. And what cancels? P. Right? Everybody see that? The P cancels? Numerator, denominator, P's gone. Jared, what was CV? It's up there on the board.
The molar specific heat,
Yeah, what's it equal to?
joules over moles per second.
No, what's the value?
Oh, 3/2.
3 halves R. So I have 3 halves R delta T plus R delta T. Oh, NR delta T. There's an N. So what do I get when I add N 3 halves R? Let's just write it this way. I can factor out what? The N, the delta T. And I have a 3 halves R plus R times delta T. Right? You with me, Miss Mary?
Yeah.
What's 3 halves R plus R? I have 3 halves plus 1, 5 halves. So I can write that Q is equal to N 5 halves R delta T, or N CP delta T. What's CP? 5 halves R. Hey, Dr. Browning, why do I have different values of molar specific heat? One at volume, constant volume, and one at constant pressure. Because this is molar specific heat at constant pressure. They're different. Why is that? What's happening to this gas when I heat it? It's getting faster, but it's also doing what?
Expanding.
It's expanding, which means it's doing what? It's doing work on the environment. So the heat I put in is not all going into the gas. Some of it's being released to the environment through the expansion.
Dissipated, right?
Yeah, well, right, it's growing. So that means I got to put more heat in to get the temperature to rise. So it has a larger specific heat. So Cp is bigger than Cv. Cv, all the energy stays in the gas. But in this process, the gas expands, and so it transmits energy back to the environment through expansion. Right, make sense? So, if you look at Cp and Cv, they're related. Cp minus Cv, what's that gonna give me?
You know what 5 halves?
5 halves R minus 3 halves R just gives me R. Okay? So these two quantities are related. Okay, so this is isobaric. All right, you ready for the next one? Okay, we kept the volume constant. We kept the pressure constant. What's next?
Temperature.
Temperature constant. Very good. And what do you think you call it?
I said something.
Iso. Okay. Isothermal.
Metric.
So we're using the word, it should be isotemperature, but isothermal is what they call it. Thermal is really more heat, but anyways, we call it isothermal for constant temperature. I like isotemp better, but that's neat. Okay.
Quick question, Dr. Brown.
Yeah.
What's the difference between CP and CV?
CP is just more specific to constant pressure.
Constant pressure?
CV is more specific to constant volume.
Thank you.
Okay. Where's my black marker? Here it is. We'll start here at P naught. V naught. Okay, isothermal, that means what? Delta T is 0, correct? So if I look at my ideal gas law, again, PV equals what? nRT. If T is constant, that tells me this whole side is constant. So when I change pressure, the volume is going to change such that P naught V naught equals P final V final. Does everybody see that? Right, because T is fixed, right? This is all constant. So P and V are related like this. So if I start here at this pressure and volume, and I expand the gas, what does the pressure have to do? Now if I make V bigger, what happens to P?
Smaller.
Well, smaller, right? And what kind of relationship is that? These are reciprocals of each other, right? So if I double V, P has to go down by,
Isn't that like they're inversely?
yeah, the inverse. So I don't get a line, I get a curve, a 1 over curve. P final. P final. So I get this 1 over curve for the relationship between P and V. Right? Because if I solve for P final, what do I have? P final equals P naught V naught over V final. So you see it's proportional to 1 over V final. Like 1 over X curve. Is what I'm getting. Okay? So this is how it changes. So this is called an isothermal. So this curve is a constant temperature. And you can imagine there's a whole bunch of these curves running through my PV diagram, and they're all different temperatures. They're all 1 over curves. Okay? So this might be like 100 Kelvin, 200 Kelvin, 300, 400 Kelvin, right? These are all constant temperature curves. Right? And I'm going down this particular one right here. Okay, let's work through this. If delta T is 0, what does that mean for my first law? What else is 0? Danny, what else is 0?
Delta T.
Delta T is 0, something else has got to be 0.
Q? Q?
Nope,
No.
not Q. Mary.
Like you.
Delta U. Because why? Delta U depends on delta T. Right? So that means delta U is 0. Okay. All right, that's cool. What does that tell me about then W? and Q.
Well, one equals a negative.
Yeah, because of the first law, 0 equals Q plus W, so Q equals minus W in this process. Okay, how do I calculate W? Integral of what? Okay, let's see if we can do that. Work equals minus the integral of P dV. All right, so I got to put P in there in terms of V, but I just use the ideal gas law, right? So this would be from V naught to V final. All right, so I get minus the integral from V naught to V final, sorry, of P, which is NR T over V times dV. Okay, I can pull out the nRT, right? Minus nRT, and I have the integral from V naught to V final of dV over V. What's that? You should know that integral.
Is it log?
Natural log, right? Dx over x is natural log. So that tells me the work is going to be equal to minus nRT ln of V final divided by V initial. Right, because you take V final minus V initial, but they're both logs, so you can make them in division. Everybody remember that from logs? Matthew, you remember that? Deep down? Okay, I'll do it for you. So I get a minus nRT times the ln of V final minus the ln of V initial. And when I subtract logs, I can write them as divided. Right, so that's the work in this process. And it's what? Blue marker. It's the area under the curve. So it's this. Okay? It's that. Okay? Okay, what's Q?
The positive of that.
What was that?
The positive.
Positive of that. nRT, ln. Be sure you do it in Kelvin, right? Because there's no delta T here. Gotta do it in Kelvin. Right. Okay, so we got isobaric, isovolumetric, isothermal. We have just enough time to introduce the next process, but we won't finish it because the next one's involved.
Do we have to like memorize all
Yes,
this?
you gotta memorize these. You gotta know these like inside and out. This is like biology class.
I can't tell if you're being serious.
No, you do. I'm serious. I'm always serious about physics.
Are you serious?
Yeah, you gotta know them inside out because guess what we're gonna do? We're gonna make theoretical engines out of these processes.
Oof.
And you can't analyze an engine if you don't know the processes. Right? So you gotta know the processes. All four. We've done 3. Oh.
And all the mathematics
where's
as
my-
well?
oh, where's my phone?
Here.
Right here.
Oh, okay.
Someone is calling you as well.
Someone
Hello?
is calling you.
Hello? Thought it was the guy coming for the interview. The salesman. You can hear that. Like, go doink. You know what I mean? You ever hear that? You get a call? You just don't answer calls, do you guys?
No. You answer calls? Like for random numbers?
Yeah. And then they go doink. If I'm in a mood, I'll like talk to them.
I mean,
You know? Or I'll say, this is Dr. Brown in his office. Like, oh, sorry, and they hang up. They're expecting, some telemarketer. It's really annoying. I get like calls for like Medicaid. I'm not that old yet, people. Why are you calling me? I got a ways to go. I'm like 50s. All right. Last process. And like I said, we won't be able to finish because this one's involved. But we can start, okay? Let's start. Let's draw isothermals first. Remember, isothermals are these 1/over curves, right? So I'm going to draw some isothermals. Kind of like that. These aren't the best drawn thing. But this process is called adiabatic. And I'm going to allow P, V, and T to all change. So none of those are zero, those changes. But something is zero. But zero is adiabatic means that this thing is thermally isolated.
Can you spell that?
Adiabatic, I think. Not sure.
B-A-T-I.
Something like that. You can look it up. Thermally isolated. What does that mean in terms of the equation? If I say thermally, like this thing, right? Let's say I brought my lunch to school. I want to thermally isolate it. Why?
Keep the temperature.
Okay, keep the temperature. But more so, I want to keep it cold, right? But how is it going to heat up? My lunch.
In a microwave.
No. If I just brought like tuna salad out, set it in my car, I'm driving around, it's in the sun. That's all why? Because it's going to absorb heat from the environment. If I thermally isolate it, I don't want it to absorb heat from the environment. All right? So that means what is zero? Q. When I thermally isolate stuff, I don't want heat transfer. That'll keep it at the same temperature, except I'm going to allow it to expand. I don't want my tuna salad to expand, so, right? But I'm going to allow the gas to expand or contract, but I'm going to keep it thermally isolated. I'm not going to allow any heat transfer. So Q is zero. Okay, Q equals zero in this process. So if Q equals zero, then what does that tell me about delta U?
Just the work.
Okay, it's equal to the work. And what is delta U also equal to?
3/2 nRT.
3/2 NR delta T, right? Or NCV delta T. So the work and then change in internal energy are equal to CV delta T. So this doesn't seem so bad yet, does it? Okay, now it's going to get a little interesting. So what does that curve look like on here? Right? If I look at the ideal gas law, PV equals nRT, what's going on? Because I'm changing all of these quantities. Right? So on my graph, it's like going from here to here. I'm going to jump isothermals. So I'm going to expand the gas, and as I expand the gas, I cool, because I'm going from a higher isothermal to a lower isothermal. And I'm changing the pressure as well. Right, so I'm dropping isothermals. Okay, I'm going to give you the relationship. And then on Friday, we're going to derive the relationship. So you can practice doing some homework if you want. But Friday, we're going to work out the mathematics of how this comes about. So I'm going to give it to you today. You're going to say, Dr. Brown, this doesn't make any sense. Where all these things come from? And I agree. But we're going to show you on Friday, okay? So the relationship is P naught V naught to the gamma equals P final V final to the gamma. All right. What's gamma? 5/3. That seems to come out of nowhere, doesn't it? Why 5/3? Huh. Have you seen a 5 and a 3 earlier in this lecture?
Yeah.
Where, Matthew?
Back with the, my brain's not with
3 halves R plus R.
Okay, a 3 has R.
Oh, that was over 5. That was 5 over.
There's a 3 halves and then a 5 halves.
Yeah. So what was the 3 halves?
CV, yes.
So CV was 3 halves R. CP is
5
5
halves.
halves R. Can I get a 5/3 out of those?
Yes.
Yeah, if I divide CP by CV.
Yeah.
Right? So gamma, which is 5/3, is actually CP over CV. I said, how does that show up in this equation? We're going to see on Friday. All right. Yeah, go ahead. Sorry to cut it a little short.